It's the early 2000s. World of Warcraft has just come out and everyone is hooked. One player is walking on the map, playing around just like everyone else. But then a thought creeps into his mind and he suddenly stops. This world only exists because somewhere a machine is talking to my game and deciding what happens next. But what if I was the one talking to the game? Every time I cast a spell or move, my computer is sending something out across the internet. On the other side, there has to be something receiving this data. There has to be a server, a Blizzard server. That thought won't go away, so he starts experimenting. What if I could see that traffic? What if I could make the client talk to something other than the Blizzard machines? From there, the idea takes over. If one packet can be understood, then theoretically speaking, all of them can. And if all of them can, the entire server can be rebuilt. That idea sparked one of the most ambitious reverse engineering feats in gaming history, recreating World of Warcraft server-side from scratch. In this video, I'm gonna break down how that experiment grew into private server projects. I'm gonna analyze the source code and how it actually works. Before we start, let me walk you through the roadmap of the video. First, I'll talk about the client-server architecture. Then we'll look at how people actually reverse engineered it. Packet sniffing, figuring out the protocol, logging packets, world packets, and so on. Then I'm gonna talk about the first project of this type, Mangoes. For the technical part, I'm gonna break down the AzerothCore project. I'm gonna start with the high-level architecture and then dive into the code to see how it really works. And finally, I'm gonna wrap it all up with some conclusions. What can we learn from all of this? Quick note. Before we start dissecting this codebase, analyzing this much code means there's always a chance I've misunderstood something or overlooked important details. If you catch any mistakes or have additional insights, please share them in the comments. Your corrections are incredibly valuable and I'm always grateful when the community helps improve the accuracy of these videos. Okay, let's start. The whole idea of the client-server architecture wasn't something Blizzard invented for World of Warcraft. That concept has been around for a while. We even talked about it in my Quake video. And before some unemployed genius in the comments starts typing a 3-page essay, I'm not saying Blizzard just ripped Quake's code, copy-paste style and called it a day, okay? Calm down, you're gonna break a nail. So, at a high level, the point of the client-server architecture is this. You don't need to run everything on every machine in order to run a piece of software. And in our case, that piece of software is a game. And when I say the game, I don't mean just the installer you run on your computer. I mean the full system that makes World of Warcraft actually work. So, if you put 2 and 2 together, that means the player only installs a part of the game, the client. The other part, the brains of the operation, lives somewhere else, on the Blizzard machines. And that's what we call the client-server split. Now, let's talk about the responsibilities of these two components. So first we have the client. The client is the program you install on your computer when you want to play World of Warcraft. It has all the data you need, the textures, the sounds, the models, basically everything the game needs to run on your side. That means that everyone has access to the original client. Private servers don't make their own client. They just reuse this one. Okay? So in order to connect to a private server, you only take the file called realmlist.wtf. Yes, this is the actual file name. And replace the official server address with the private one. And that's it. Suddenly your game talks to a completely different world. Now, in case you're wondering about copyright, all the copyrighted material like the images, models, sounds, that's all in the client. The server itself is just numbers and rules, so to speak. And that's why private server code is generally fine to share for educational purposes, as long as you're not redistributing the client. So what does the client actually do? Well, pretty much everything you can see and hear. It renders the graphics, handles your input, talks to your computer, and even does some client-side prediction. Okay, now let's talk about the server. The server is the hidden part that Blizzard runs on their machines. Nobody, and I mean nobody outside Blizzard has the code. It's not public. And unlike the client, it doesn't need the game data because it's not rendering anything. What the server does have is the rules of the game, and it holds the true state of the game. It takes all the inputs from the players, enforces the rules, runs the simulation, and then sends the updated game state back to the clients. If you've seen my Quake video, you'll recognize a similar silver lining. The client renders and the server enforces the game state. World of Warcraft just takes that model and scales it to something massive. Now, what can we learn from all of this? You will probably never work on an MMORPG game, but at some point you'll probably deal with distributed systems, software that runs across different machines. And then you'll face the same architectural question Blizzard did. How do I split responsibilities to make the system efficient with as little overhead as possible? For the server, everything is just numbers. It doesn't need to see graphics. It only cares about the rules and inputs. And that exact decision, separating the data from the logic, is what made private servers possible. Think about it. If the client already has all the game data and it just sends inputs to a server, then in theory, anyone could mimic the server's responses and trick the client into thinking it's talking to Blizzard. Do that perfectly, and the player can't even tell the difference between a private server and the real thing. Which leads us to the key insight. If you speak the communication protocol, you can rebuild the server. If you speak the communication protocol. But the thing is, Blizzard never published documentation for that protocol. I mean, private servers were never meant to exist in the first place. So, how did the developers figure it out? How did they reverse engineer this whole thing? So, how do you even reverse engineer something like the server side of World of Warcraft? Blizzard is a huge company with many employees. Rebuilding it from scratch is not something a single developer can just decide to do on a weekend. Think about it. Every NPC has to be placed, every loot table filled out with drop chances, every spell and boss mechanic has to be figured out. It's an insane amount of work. You don't have to be a genius who worked at Blizzard and the cheating squad to realize that this is a huge task. I mean, just because of the sheer volume of data you have to reverse engineer. Now, the starting point for the reverse engineering was packet sniffing. When you play World of Warcraft, your client is constantly talking to Blizzard servers. Those messages can be captured, and once you have the traffic, you can start looking for patterns, like login, casting a spell, killing an enemy, and then you can see what packets get exchanged. Now, how do these packets actually look? No matter the medium, TCP, UDP, or even radio communication, it always follows a structure. You'll typically see a header with some metadata and then the payload, things like the ID, arguments, state updates, and so on. That's how the client and server align on the communication. And I can imagine that at first this reverse engineering was very rough. You capture traffic, make guesses about what certain packets mean, and then try sending something back just to see if the client reacts. So over time, they built tools to parse and analyze this data, gradually mapping out the protocol that Blizzard never shared. And once you understand the protocol, you can start emulating the server. That's where the real grind begins, recreating the logic behind every rule of the game. And that's also why the early private servers in the 2000s felt so buggy and incomplete, because they were. I remember my friends talking about them, but I never actually played World of Warcraft, mainly because of the monthly subscription. In my hometown, we just didn't have those prepaid cards, so it wasn't even an option. And honestly, most of my friends were playing Dota, which I started playing around 2007. Dota was basically the only game I have played for more than 10 years, and I have friends who are still playing it to this day. Anyways, back to the topic. People realized that if you can mimic Blizzard servers closely enough, you could trick the client into thinking it was the real thing. And that's when people started the first open source private server project. So in 2005, the Mangoes project started, Massive Network Game Object Server. The goal was simple but insane: re-implement the server side of World of Warcraft. Developers captured packets, mapped opcodes, and slowly figured out the message format. Under the hood, Mangoes ran as two processes, a login server and a world server, and it used databases to keep data persistent. Auth for accounts and realms, characters for inventory, skills, guilds, and mail, and world for creatures, quests, loot, and scripts. Then at some point, Mangoes got forked into Trinity Core, where they improved the packet handling, added more scripting, and support for multiple versions. But it still ran the classic split, AuthServer and WorldServer, with the same databases. Trinity Core grew a big community and became the most widely used base. Later on, from Trinity Core, another fork emerged, AzerothCore. It focuses on Wrath of the Lich King and tries to make extending the server easier. Same model, same databases, but with a modular system where you can create your own modules without touching the core engine. This modularity plus good documentation made it very popular for people who wanted to understand the architecture and add custom content. Now, it's important to mention that AzerothCore also reused code from Sunwell Core when that project shut down. And if you trace the ancestry back, the path looks something like this: Mangoes, Trinity Core, Sunwell Core, AzerothCore. Now, for the code analysis in this video, I decided to focus on AzerothCore. I could have picked, of course, any of these. None of them is a clear winner in every aspect. I went with AzerothCore for a few reasons. It's actively updated, the documentation is decent, and while I didn't dive deep into the community, it didn't give me the ask one wrong question and get roasted like on Stack Overflow vibes. And most importantly, architecturally speaking, it has some valuable ideas, like its modular design and the clean split between the core and the modules. Okay, now let's talk about AzerothCore. We're gonna start with a high-level view, software architecture, components, and then gradually go into the internals and technical details. I'm gonna leave all the links for their homepage and Git project in the description. So let's start with the architecture. AzerothCore runs as two separate programs. We have the AuthServer, which handles the logging and realm list, and we have the WorldServer, which runs all the gameplay subsystems. On our side, the client expects two connections. The first one is with the logging server. The default port is 3724, and this is used for the authentication. The second one is with the WorldServer on the default port 8085, and it's used for character selection and the actual gameplay. Underneath this, there are three main databases. So we have the Auth database, which is used for accounts and realms. Then we have the characters database, which is used for player saves, inventory, guilds, mail. And then we have the world database, which is used for the quests, loot, and so on. Now, besides that, we also have the modules and scripts that plug into the core. During gameplay, most of the state lives in the RAM, and only specific parts get written back to the database when needed. As you can see, there is no direct communication between Auth and the world. They coordinate through the Auth database, which only tracks things like realm status and player counts. This is the static view of the architecture, the components and how they fit together. But to really understand how it works, we need to look at the communication between the client and the two servers, the AuthServer and the WorldServer. Before I dive into the source code breakdown, let me give you a general overview of how the communication flow works. From my experience, it's always better to start with the big picture first. A simple diagram covering just the essential components can save you a lot of confusion later when we get into the actual implementation details. Let's first go through the login scenario. I'm gonna talk about the classic login procedure used up through version 335A. Why is it important to mention this? Well, Blizzard changed parts of the login procedure in the later versions. Okay, so in the Wrath of the Lich King, the login works in 3 steps. First, we enter the username and password. This gets us the realm list. Second, we pick a realm. That gets us to the character screen. And lastly, we pick a character, and then we enter the world. You can always go a step back, but each step builds up on the previous one. But how does this actually work? Before we start talking about the packets, it's important to mention that we differentiate between 2 types of packets that the server and client are exchanging. We have the login packets and the world packets. The login packets are used for the login routine. And then we have the world packets that are used to exchange in-game information. Okay, so once authenticated, you land on the character screen. On the character screen, there's a few things that you can do. This state machine diagram shows it really good. So you can delete the character, rename it, create a new one, or log in, and then end up in the world. This login procedure is handled entirely through login packets. Now, when talking about state machine diagrams, I know people that would rather spend 3 hours in a meeting discussing why they will not deliver you a state machine diagram with their specification instead of drawing out the diagram in 2 minutes in Paint. And then you get like 3 developers interpreting the same set of requirements in 3 different ways, and the genius who wrote the requirements wanted something completely different. But God forbid someone has to draw a diagram. Okay, that was a high-level view of the logging procedure. Now let's talk about how the client communicates with the world server. The client sends data. The server socket, WorldSocket, reads the header, builds a world packet, and looks at the opcode. The opcode is looked up in a central table in the opcode source code. The table says, for this opcode, call this function on WorldSession, which is your per player session object. That drops into a handler, and the handler then calls the gameplay code that actually owns the rules for that thing. For example, you press W, the client sends a world packet containing the header and the movement opcode. The world server reads it, resolves the opcode, and starts the right handler. Then the movement data is validated for basics like speed and boundaries, and then your position is updated in memory on the server. The server then pushes updates to nearby players so they can see you move. It doesn't update the database on every tick. Your last position gets saved on the logout or at save checkpoints in the characters database. Now, by the same token, every other action is resolved. If you cast a spell, the server resolves the spell opcode and starts the spell handler. Now, a quick clarification about the databases: not everything is stored in them. They're mostly for persistence, the stuff that needs to stick around after you log out. For example, your character's inventory, gold, talents, guild, and so on. But things like real-time combat aren't constantly written there. Now, in this video, I will not talk in detail about modules and scripting, but it's important to mention that AzerothCore is built to be easy to customize without hacking the engine itself. There's a script layer with hooks like player script, creature script, spell script, world script that trigger on certain events. And then you can also add custom modules in the modules folder, and each can have its own C++ code and configs. The build system then picks them up automatically so the core stays clean. That makes it easy to separate what's engine code and what's an add-on. So that's the top level view of how the client talks to the 2 servers. First the login and then the world, all through packets going back and forth. Now that we got the big picture, let's zoom in and see how AzerothCore actually implements this under the hood. But keep in mind, AzerothCore is a massive code base. Covering every single line would take hours, and I don't think anyone wants to sit through me reading C++ like it's an audiobook. So I'll just focus on the interesting parts. If you're one of those people who actually does want to analyze everything, congratulations on being insane. But don't worry, I put links to the source code in the description for you. Okay, now let's actually walk through the source code and the order things happen. We'll start from the beginning. How the servers boot up, start listening to their ports, and then catch packets from the client. From there, we'll see how those packets get decoded into opcodes, and finally how the server handles something concrete, like a movement opcode or a spellcast. Quick reminder, in this video I will not analyze the databases, optional modules or scripting. If you really want me to, I can make a second part. But let's be real, this project has been worked on for, 2 decades. And you expect me to dissect every single line, cover everything with bulletproof analysis in like 2 weeks, while also working a full-time job. Yeah, sure, let me just call my coke dealer. My goal here is to cover the big picture and then dive into the most interesting parts, not write a compendium. Also, if you got any suggestions for what project I should cover next, let me know in the comment section. And if you like the content, feel free to share it on any platform, Reddit, Twitter, X communities, Discord channels, or whatever. Okay, let's continue. One thing to keep in mind, the AuthServer and the WorldServer are two completely separate programs. Each one has its own main function, its own process, and its own job. And yes, two main functions. It's not a bug. Okay, so you can download the source code from the AzerothCore GitHub page. The link is in the description. When you download the code, you will see a bunch of folders. We are looking for the Auth and WorldServer code. So that's located in source, server, apps, and then you see the split. I'm gonna start with the main of the AuthServer. Okay, so this is the main entry point for AzerothCore's Authentication server, the gatekeeper service that validates player logins. So what it does is it starts up, loads the configuration from the AuthServer config, and establishes a connection to the login database. It then opens a listening socket and waits for the players to connect. When players attempt to log in, it validates their credentials using the SRP6 protocol, checks for bans, and provides a list of available realms. So it basically keeps doing this and also keeps tracks of banned players until it receives a shutdown signal. Now let's go through the code. Okay, so the current server process type is set to server process auth. This is some kind of enum. Yeah, so you can have two process types, auth or world. Let's go back to the main. Now, if you're wondering why do we need to identify the process type, well, AzerothCore runs multiple server types. They share a lot of code libraries, but they do need to behave differently. For example, the AuthServer doesn't need spell mechanics and the WorldServer doesn't need a logging behavior. By setting these types, you're putting like a name tag on this process saying, hey, I'm the AuthServer, so shared code knows how to behave. Now, I'm guessing when we go to the main file of the WorldServer, we will probably see the same line, but let's continue now. So this line of code is setting up what's called a signal handler. It takes two parameters. First, which signal you want to catch, that's the abort signal in this case, and which function should handle it. In our case, it's the abort handler. This ampersand just gets the address of the function so the signal knows where to find it, okay? But what even is this? This sig abort is an abort signal. It gets sent to your program when something catastrophic happens. For example, like a failed assertion or some critical error. Normally, when your program receives this signal, it just terminates immediately. But this line registers a custom function to run first. So instead of just crashing when sig abort comes in, the program will call this AzerothCore abort handler before it dies. It's basically your program's last chance to do something useful before it goes down. For example, people use it to capture stack traces, memory dumps, error messages, and generally speaking, this is very good for debugging. Because imagine your program crashes and you have no clue what happened right before the crash. Okay, let's continue. Then we have the configuration and the command line arguments. Generally speaking, every server needs configuration. We need a database, credentials, network ports, or some other stuff like, I don't know, security settings and so on. Now, instead of hard coding these, which is a terrible idea by the way, we load these from the AuthServer config. This allows server admins to customize their setup without recompiling the whole code base, okay? So it decouple the executable, the binary, from the configuration. You make it with parameters, so to say. For example, you want to run it on port 8080 instead of 3724. You just need to edit the config file and not recompile everything. Okay, the command line parsing gives you the ability to build in some small helper tools for showing info like help or version, so you can check easily which version you're looking at without needing to run it. This early exit on help and version is very smart because why initialize databases and networks if you just want to see the help text? Okay, then we add the file and arguments in the config. Then we have the configuration manager. This lower S in front of it can either mean server or sometimes it means singleton. And I mean the singleton design pattern. This depends, of course, what naming convention the project is using. I mean, it can mean both if people are not following the convention, okay? But let's take a look at it. Okay, so sconfig manager is a macro that expands to config manager instance. So this line is really calling config manager instance configure. Now, if we go inside config manager, okay, these are very good indicators for my assumption. Let's go inside this instance function. Okay, so yes, config manager instance returns a pointer to a config manager object. But here's the trick. It's always the same config manager object, no matter how many times you call it. And if we go back now to the header file, you will see that the constructor is private. Since in classes everything is private by default in contrast to a struct where everything is public by default, that means that this config manager class is designed as a singleton, which means there can only be one instance of it in your entire program. You can also see that the copy constructor and the assignment are deleted too, so you can't duplicate it. Therefore, the only way to get a config manager is through this instance method. And inside the method, there's a static variable that gets created once on the first call and then it's reused forever. But now let's zoom out a bit. Why would you make it a singleton? Well, configuration management per se is something you want centralized. You load your config file once and then every part of your program needs to access the same settings. If different parts of your code have different configurations, then it doesn't make sense having a configuration at all. I mean, everything would be a mess. But with this singleton pattern, everyone's guaranteed to be looking at the same configuration. Okay, then we have this check to see if the configs are loaded. If not, then we just terminate it. Then we initialize the logging. The logging, generally speaking, is the black box recorder of your server or whatever software you're building. If something goes wrong, you can always go in there and investigate the problem. Now, generally speaking, what I would recommend you, before you even start programming your solution, your software, think about stuff like logging. It will help you immensely when it comes to debugging, okay? Let's continue. Then we have this. The first line loads OpenSSL providers, so basically telling OpenSSL load both the modern and the legacy crypto modules. But now the second line is where it gets really interesting. This is using the shared pointer in a clever way that has nothing to do with managing actual memory. Let's break this down. So the shared pointer is creating a smart pointer. But let's look at the constructor parameters. The first one is a null pointer, so we're actually not pointing to anything, to any real object, and therefore the shared pointer is not managing absolutely nothing. But the magic happens in the second parameter. This is a lambda function that becomes a custom deleter for the shared pointer. So the lambda syntax says this is the capture list, which is empty. Void is the parameter, the null pointer being quote unquote managed. And this OpenSSL crypto threads cleanup is what actually runs. The lambda ignores the void pointer parameter and just calls the cleanup function. So when OpenSSL goes out of scope, it will automatically trigger this custom deleter, which is the lambda function. This happens no matter how the program ends. Normal shutdown, crash, exception, whatever. The C++ stack unwinding process guarantees that the deleter runs. It's basically hijacking SharePointer's automatic cleanup mechanism to guarantee that those open SSL providers get properly unloaded. Pretty clever way to use RAII for guaranteed resource cleanup that isn't even memory related. Okay, after setting up the OpenSSL stuff comes the AuthServer PID file creation. The first line attempts to grab the path name with the configuration manager. If you haven't specified one in your config file, it gets an empty string and just skips this whole section. So PID files are optional. But if you have configured a PID file, then it tries to create the file. So create PID file returns the process ID if it succeeds, and it triggers true. But if the creation of the file fails, the server just gives up and exits immediately. It doesn't try to continue without one. This ensures that if you specifically configured a PID file, you probably need it. And if you can't access it, then there's no point in continuing. So it refuses to start the server at all. Okay, let's continue. Here we initialize the database connection with startDB. StartDB uses a database loader that takes the global login database. The AuthServer needs this database to store account credentials, ban list, realm information, and session data. This is persistent memory, okay? Now let's go back. Then we have the secret manager. This is again a singleton, and it initializes the encryption stuff. Then we have the IP location, which loads the IP location database. Okay, here we have the same cleanup trick as before. So when db handle goes out of scope, it automatically calls stop-db to close the database connections. Then we get the realm list. Again, we have the same shared pointer cleanup trick. We have this realm list check. The realm list is, if you don't know what it is, it's the server browser showing which games you can enter. And if there are no realms configured, there's no point in authenticating players if there's nowhere to play. Okay, let's continue. Seems like you can configure a dry run, which is good if you just want to test something out. So what is a dry run? In a dry run, you would configure everything and it would run up to this point, and then it would just terminate without running the rest of the program. And then this is where the network listening gets set up. We have the start network function. Let's go in there. And this is the key line. This registers with the IO context saying when someone connects to port, the default port is 3724, call onSocket accept to handle their authentication request. Then we have a keep database alive handler and a ban expiration handler, but so far nothing is actually running yet. We've just registered a bunch of callbacks saying when this event happens, call this function. And finally, we arrive at the IO service worker loop. Now everything starts happening. So run is the main event loop that is checking, did any data arrive on the port, call onSocket accept to handle the player login, or did the ban timer expire, call the ban expire handler, and so on. So all these async wait calls, we're just setting up the callbacks. Run is what actually monitors for those events and dispatches to the right functions when they happen. So this function blocks here until someone calls the IO context stop, which happens in the signal handler. Okay, that's the main, which is very dry to read. Now, let's take a look at the AuthSession file, which will give us more insights how the authentication actually works. Now, this is the core authentication session handler. When a client connects to the AuthServer, it creates an AuthSession instance that manages the entire authentication. The client first sends a logon challenge with their username. The server responds with cryptographic parameters. The client then proves it knows the password by solving a mathematical challenge. And if successful, it receives a list of available game servers. For reconnections, it then just reuses the existing session key. Okay, let's go through the code. These are opcodes, so each packet from the client starts with one of these. It's basically like a state machine. Challenge comes first, then proof, then you can request realm lists. If you're wondering where do these values come from, well, it's just what the official game expects. So they use the values from the sniffed packets. This is defining the network packet structure that the game client sends when a player tries to log in. This line tells the compiler, don't add any padding between struct members. Normally, compilers add extra bytes between struct fields for memory alignment optimization. But for network protocols, you need the exact byte layout that both client and server agree on. Now this static assert, this is a compile time check, making sure the struct is exactly the expected size in bytes. In case the compiler adds unexpected padding or someone changes the struct, the compilation will fail. It's basically saying this packet must be exactly 33 bytes, no more and no less. So this pragma-pack push 1 at the top ensures this will work by eliminating any padding the compiler might add. Now, another interesting thing is this unsigned integer 8i with the size of 1. This is a clever C trick that is used to handle variable length data at the end of a struct. The I1 declares an array of size 1, but it's not really meant to hold just 1 byte. It's a placeholder that lets you access whatever data comes after the struct in memory. So when the client sends a login packet, it looks like this in memory. The I_length field tells you how long the username is. Let's say someone's username is Tariq, 5 bytes. The client sets I_length at 5 and then puts the 5 bytes of Tariq right after the struct. Even though I is declared as size 1, you can access the indices 2, 3, 1, etc. to read the actual username bytes. The compiler doesn't bounce check this. So the fifth element, the I index 4, would give you the Q from Tariq. It's basically a way to have a struct with a variable size string at the end. The struct itself has a fixed size, but the actual packet can be longer depending on the username length. I mean, there are many other ways how to do this, but this is old school C network programming, where you need precise control over the exact byte layout that goes out. Okay, then it continues with defining these structs. Okay. And then at some point we arrive at this, init handlers. Okay, so first let's understand the syntax. Unorder map is basically a hash table or dictionary that lets you look up values using keys. Here in this case, the uint8 is the key type and auth handler is the value type. This creates a lookup table mapping packet types to their handlers. The entries in the square brackets specify the key you're storing under. The curly brackets part uses brace initialization to create an auth handler object with 3 values: expected status, expected packet size, and the function pointer to the handler method. So when the server receives a packet from a client, it looks at the first byte, the command field from that packet structure, to figure out what kind of packet it is. If a packet comes with a command auth logon challenge, the server can do a quick lookup in this map and find the right handler function. So this creates a global constant map with all the handlers preloaded. Now when packets arrive, the server can instantly do handlers packet type to get back the handlers info for that packet type. It's basically building something like a phone book where you look up a packet type and get back the function that knows how to handle it. The account info load result part is separate. It's taking a database query result and loading account information like username, band status, and this part is also interesting. So they use a function to convert it to uppercase. Okay. Then we have this weird ass looking line. This is some C++ gourmet shit. Python developers, send your kids in the other room now. Okay, this is the AuthSession constructor implementation. If you go to the header file, you will see that the definition in here, but more importantly, you will see this. AuthSession inherits from socket. Now, if we go back to the constructor, it makes sense or more sense. So when you create an AuthSession object, you initialize both. First, you initialize the socket part. So you call the parent constructor. And then you set the AuthSession specific parts like build and version. This just shows you how they really thought it through with the implementation. You could, of course, make AuthSession completely separate from the socket, but by doing it this way, you can reuse socket as a base class for multiple child classes. So I guess AuthSession is not the only class inheriting from socket. And I mean, this is a very minimal and trivial example of how good this code base is. Everywhere throughout this project, you will see very nice tricks and elegant ways to solve some problems. Anyways, let's continue. Then they start with implementation for the specific authentication routines like start, update, reading packets, sending packets. So when starting, it gets the IP address, logs some stuff, then you get data from the login database, and then you call the check IP callback. This is now important. So as you can see, we haven't processed any packets really yet, but we call the check IP callback. So what this does is, before you even receive the username of a client, you first check the IP. Why is that? This is a protection measure. There is no point in processing the packets from a banned IP address, and people get banned for various reasons, but a big one is DDoS attacks, or if the Blizzard guy catches you being a naughty boy. So yeah, first check the IP, and then we're gonna talk. If we go in the callback, you can see that if you're banned, it creates this packet byte buffer, fills it with an opcode, which we can see as the header of the message, and then comes the payload. We send out the packet, and you just get a polite, take your ball and go play elsewhere. This async read in here is important because you don't want to block other connections while checking the database, but I'm gonna talk about it later in more detail. Okay, so then we got the functions for reading and sending packets. This is something that always follows the same logic, doesn't matter what you're working on. You have to check if the socket is open or closed, and then you read or send bytes until you reach the end of the payload. So you basically check status and then iterate through the packet. You can see here, get read buffer to get the starting point, get size so you know when to stop, and then you do things. Same goes for sending, but in the other direction, of course. So if the socket is not open, I guess this has to be a socket function, yeah? So if it's not open, there's no point in sending packets, just exit. Then if the packet is not empty, create a buffer with the packet size and start writing the contents in the buffer. And finally, you move it to the queue. Okay, these are the basics. Checking for IP bands and reading and sending packets. Now, a general observation from my side, if I take a look at how this is structured, you can see that for every expected message from the client, you have a specific handler. In every handler, you have a corresponding callback function. And in the callback functions, the data packet gets created and filled with data. For example, you have the handle logon challenge. It does a bunch of stuff and then at some point calls this query processor and adds the callback. Logon challenge callback. But why do they do it this way? They are solving the problem of blocking I/O, which would kill the server performance. Database queries are slow. If the server waited for each database response, it would freeze every time someone logs in. Player A sends their username and the entire server stops responding to everyone else until the database comes back. So they split it into two parts. A handler that starts the database query and immediately returns, and a callback that gets triggered when the database responds. It's important to understand that each player has their own separate AuthSession object. When the callback is created, it's tied to that specific player's session. So when database results come back, they go to the correct player. Player A's results go to player A's callback. Player B's results go to the player B's callback. So the handler kicks off the database request, the callback finishes the job. This keeps the server responsive while still handling authentication properly. Okay, now the rest of this AuthSession code is handling the client requests, SRP6 protocol, reconnect routine, providing the realm list, client version verification, and so on. Now, another observation from my side, the SRP6 implementation is rock solid cryptographically. Even if someone steals the entire database, they can't recover passwords. They can only steal verifiers that are useless without original password. Now, from a security standpoint, it would be interesting to try, for example, to see how secure the versioning checking is and if you can bypass it. Or, for example, you could make a proof of concept to see what happens if I try to use someone else's session key to quote unquote steal it and then try to reconnect as them to see just what happens. Okay, now let's take a look at the code of the WorldServer. Before we continue, a word from our today's sponsor, Brilliant. Instead of looking at the weather app at parties or scrolling through your phone settings at the airport for no reason, just get Brilliant. It has interactive lessons on all kind of stuff that make your brain take a break from doom scrolling. I use it when I feel stupid from breaking production, again, or when I need to look smart in front of people who don't know that I have a YouTube channel. Anyways, the cool thing is you don't need to be a genius to start. Brilliant builds concepts up gradually, so even if social media has destroyed your attention span, you can still handle it. To learn for free on Brilliant, go to brilliant.org/Tariq10x, scan the QR code on screen, or click on the link in the description. Brilliant also gives my viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant. Now, back to the video. This is the main entry point for the WorldServer. This runs the actual game mechanics, dungeons, raids, and synchronizes everything between all connected players. The file starts with the freeze detector, so the game is detecting continuously if it hung itself, and then after a time limit, it starts some routine where it voluntarily crashes so you can restart the game. But now let's start with the main function. If you haven't been on your phone while playing this video in the background, you will recognize this whole section from the AuthServer. So we're just gonna skip that part. Okay, now this is now something non-trivial, let's put it that way. And I can already tell it's a lot to unpack. So this block is only compiled if the AC AzerothCore platform is Windows. This is a preprocessor condition. Now, in some of my other videos, people started foaming when I said this is a very easy and clean way to add platform-specific part of the code inside a file. I was analyzing Doom or something. It was something from the 90s. Like, imagine judging how people did something 30 years ago by today's standards and feeling smart about yourself. Talking BS like, if you think this is clean, then you have no clue, I split everything into separate files and that's so much cleaner than la 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 la. In my opinion, if it's a small section, I like it more this way than splitting everything in separate files. Why? Well, if someone is fixing something, he will already see that this thing has platform specifics that you also need to fix. A separate file is easily overlooked, especially if you have bad file naming conventions. And that's where the small details kick in that separate a good project from a bad one. Why should we care about file names or variable names? It's a skill issue if you don't understand what variable A1 stands for. I'm not even arguing with people anymore, in real life and especially online. You do you, boo-boo, okay? And I can recommend this to everyone. Just stop arguing, that's it. Okay, now let's continue with this section. So I'm gonna try to explain on a very high level what this does, without going too deep in the details. I mean, I could make a full video with only these 10 lines of code probably. Anyways, they want to set a new time resolution. So what they do is By the way, this is the same trick as we've seen before, the shared pointer custom deleter lambda function. They really seem to love this trick. So they load the shared library, WinMM, that stands for Windows Multimedia.dll, and want to delete it properly when it goes out of scope. And during the deletion process, so if you have a new timer, they want to reset the timer to the default value, okay? Now, if the WinMM is loaded, it continues with setting the new timer resolution. In order to determine to which resolution to set it, they make this compare here to find out what is the best resolution. So you have this nested min-max function. All of these time begin, time get, and so on functions are all functions from the loaded DLL file. And when that's done, we got a new time resolution for the server. Now, why do we need this? Well, if the default timer resolution is too big, the game will not work smoothly and probably not work properly. We need a specific tick duration. Okay, let's continue. The following section is also similar or the same as in the AuthServer. We initialize the login procedure, we do the open SSL thread setup, and here we do a PRNG seed. P stands for pseudo, so pseudo random number generator. If you're wondering how can random be pseudo random, there is a difference between pseudo and true random. True random, for example, has to be seeded with a real noise generator. Anyways, again, same stuff like in the AuthServer setup. Okay, then we have the world update loop. This is the game's heartbeat. Each update call advances the entire world, the player actions, NPCs, spells, everything. And this diff parameter is the tick. It ensures time-based calculations to stay accurate regardless of the server load. Okay, so that's that about the WorldServer main function. Now let's trace what happens when a player presses, for example, a key to move the character forward. We will follow a packet from the client through the entire server pipeline. Okay, let's imagine we are sending this packet from the client to the server. We have the encrypted header and then we have the payload. Now everything starts with the read handler. It checks if the socket is open. If it's closed, it terminates. If it is open, it continues. And now the handler starts accumulating the bytes into the header buffer. There are some checks in case something goes wrong. When the header buffer is fully populated, we start the read header handler. Now, the read header handler has the responsibility to decrypt the header. We have some endian conversion, and now we subtract the header command size from the header size. And then we resize the packet buffer to that size. Keep in mind this is the packet buffer, not the header buffer. But why do we do that? Well, the decrypted header contains information about the packet size. We have this reinterpret cast, which I've explained in one of my previous videos. And okay, if everything went fine, the function returns true, which then brings us back to the read handler, where the function continues. Now, if we have resized the packet buffer properly, we get into this section here, where we then populate the packet buffer with the data received. And then the read data handler starts. In the read data handler, we again do some reinterpret casts. This basically reinterprets the data bitwise. We determine the opcode. Then we create a world packet with the packet buffer. And now I'm obviously skipping some details here, don't get mad at me. And at some point we land in this switch case with the opcode. Since we don't match any of these cases, we'll end up in the default case, which puts the packet into the queue. So packet to queue, which is a pointer by the way in case you lost track, we set packet to queue as a new world packet with the packet data. Then at the end of the function, our packet gets queued into the world session. This handoff from WorldSocket to WorldSession is part of the system's two-layer architecture. WorldSocket handles the network concerns, TCP connections, encryption, packet assembly, while WorldSession manages game logic, player state, opcode handling, game rules, and so on. Now, on the WorldSession side, we have the session processing. So it starts with checking if the player isn't idle for too long and then kicking people. Then we arrive at the while loop that pulls packets from the receive queue one by one and looks up the handler for each packet type in the opcode table. If we go now into the opcodes file, you will see this opcode table where each opcode is linked to a handler. I'm not gonna go into detail how the table is built, okay? So we have the opcode client and the client opcode handler. The packet has an opcode. The code looks up the opcode in the global opcode table to get the handler information. Then we have this max packet limit at 150 to prevent people from flooding the server with packets. We have some DOS protection, and finally we get to evaluate the opcode. And at some point we end up in the switch case here. Once the status check passes, ophandle call is executed. This calls a function that was pre-registered in the opcode table during server startup. So each opcode has a specific handler function. So for example, movement opcode has a movement handler, handle movement opcodes. This call function is basically a wrapper that takes the data, parses it into the right format, and then calls the right handler. In this case, we end up, for example, if we made a movement, we end up in the movement handler. All the handlers are located in the handlers folder. So server, game, handlers, and then movement, for example. And this is where the movement opcode is then processed. So that's how opcodes are processed. I could literally go for hours and hours through this code and still not cover even 2% of everything. In case you're interested in this code base, I am sure you can join their Discord and just talk to people. Or maybe try to compile and run it on your own machine. Or why not become a contributor and solve some tickets? I know it can look scary if you're a beginner, but trust me, in every project there are tickets that even beginners can solve. Just get involved, trust me. Okay, let's wrap this up with a few personal thoughts. What started as a small idea, probably in someone's basement, turned into one of the biggest reverse engineering projects in gaming history. And don't confuse reverse engineering with decompilation. These folks didn't have a server binary they decompiled, they captured packets and figured out how things work. Another big point is they didn't build a giant lookup table where, for example, client sends A, server replies with B. They rebuilt the actual game logic behind it. And they did it in a way that's extensible. You can fork the project, add features, or write modules without touching the core. If we take Mangoes as the starting point, this thing has been maintained for about 2 decades. That says a lot. Sure, it's been refactored over the years, but if a codebase is truly bad, you can't refactor your way out of it. There is a point of no return. Cross it and your only option is to start from zero again. Plenty companies hit that wall. They're not building on the shoulders of giants, or even on their own shoulders. Every few years they trash everything because a senior engineer promised a deadline that 10 other engineers said was impossible. The project ships on time and then it's truly finished. As in, you can't touch anything without blowing the whole thing up. Looking from that perspective, these projects are serious software engineering. A lot of profitable companies would be proud to ship something this organized. Now, the not so good part is there are many private servers, many forks, and tons of bug fixes that never flow back to the main projects. For example, one server fixes a spell, another fixes pathfinding, someone else scripts a raid perfectly, But there isn't one definitive build with all those fixes in one place. I mean, it's not ideal. In a utopian world, everyone upstreams everything and we all get a better experience. In reality, this is easier said than done. If you don't believe me, try organizing, I don't know, a birthday party and invite 6 of your friends. You will not be even able to find a date where nobody is busy, besides the fact that I don't have 6 friends. I didn't even have 6 friends in school. This project also proves that you don't need a $1 billion budget or work at Blizzard to create something meaningful. People get weirdly obsessed with who works at what company, as if passing one interview magically makes you a better engineer. Sometimes it just means your dad works there. I know plenty of developers who walked away from big checks just because they don't want to play the corporate game. They would rather work at a tiny, unknown company, code for 6 hours and go home without putting on a charade. And the best developers that I know are exactly those kind of people. So if there's one takeaway from this video, it's this. Sometimes you just need to do something for fun to see if it's possible. Start by asking, how does this work? And be curious enough to, I don't know, capture a data packet. And this is not about data traffic, it's about how you live your life. Don't be afraid to try something because someone might laugh. I can guarantee you, nobody is even watching, just like some of my YouTube videos. And even if they are, why would you give them the power to ruin your experience or stop you from doing something? If you want to skateboard, go skateboard. If you want to make a game, go make a game. Maybe you won't make a great game and that's completely fine, but it will teach you to try new things. And with that habit, at some point you will try something that actually clicks and takes you places you didn't expect. I want to take the moment and say a big thank you to my Patreons and YouTube members. If you want to help me get better equipment, you can become a Patreon. I dropped the link in the description. Also, only 8.5% of my audience is actually subscribed to the channel. So if you like the content and listening to my low GDP country accent, a like and subscribe would really help a lot. Okay, so that's it for today. Thanks for watching and see you in the next one. Tariq 10x.